This is video 34. In this video, we give the proof of the reset lemma, which is the second of the 4 macroscopic lemmas. The proof is in 3 parts. We start by a preliminary result. Consider an exposed path assembly P. We suppose that this path assembly grows to the north of the seed and then comes back near the seed. Consider the difference between the maximum y-coordinate minus the minimum y-coordinate of the path assembly P. Now consider the difference between the y-coordinate of the last tile of the path assembly and the minimum y-coordinate of the path assembly. We have shown in the previous video that if this value is equal to 0, then the path assembly P does a U-turn. We improved this result here. Consider the following lemma and the following inequality. If this inequality is satisfied, then the path assembly P does a U-turn and then it is pumpable. In order to prove this result, suppose that the inequality is true. We obtain a lower bound on the number of tiles visible from the west. Among these tiles, some may be hidden by the seed and some may be directed to the south. The number of visible tiles of the first kind is bounded by the size of the seed. If there are more than 2 times the size of the tile set visible tiles of the second kind, then the path assembly P does a U-turn. This result was shown in the previous video. Thus we obtain a lower bound on the number of visible tiles directed to the north and not hidden by the seed. Let's divide this number by 2 times the size of the tile set. We obtain that there exists a certain tile type and an exit direction which are shared by a great number of visible tiles directed to the north. Then we can find a visible candidate segment of direction V such that the y-coordinate of V is huge. In fact, this y-coordinate is huge enough to apply the U-turn lemma and to prove that the path assembly P is pumpable. Now we prove the reset lemma. This proof uses recurrence. We start by the result used to deal with the recurrence. This result requires a lot of hypothesis. First, we consider a simple path assembly P and a seed which both belong to the first quadrant of the plane. Then we consider a distance λ1 such that the seed belongs to the square of width λ1. We denote by W the window of this finite area. Note that the size of this window is bounded by 4 times λ1. Now, we consider a second distance λ2 which is greater than λ1. We represent here the square of width λ2. Finally, we consider a third distance λ3 which is far greater than λ2. We represent here the square of side λ3. The function psi prime used to define λ3 is defined later. Now consider 2 indices I3 and I4 such that the tile Pi3 is not inside the square of width λ3 and Pi4 is inside the square of width λ1. In this example, the first highest tile PT can be used as Pi3 and the last tile can be used as Pi4. These hypotheses show that the path assembly P grows far away at the seed and then comes back near the seed. Note that, in this example, the path assembly P exits by the north side of the square of width λ3. Without loss of generality, we can assume this is always the case. If these hypotheses are true, we aim to show that either the path assembly P is pumpable or there exists 2 indices I1 and I2 such that the tile Pi1 is not inside the square of width λ2, the tile Pi2 is inside the square of width λ1, and the number of intersections between the path assembly P shortened at index I2 and the window W is strictly less than the ones with the path assembly P. The idea of this lemma is that if the path assembly P is not pumpable, then it can be shortened into a path assembly which grows at distance λ2 of the seed and then comes back at a distance less than λ1 of the seed. By applying this result several times in the last part of this video, we will obtain the reset lemma. Without loss of generality, we can assume that the tile PT exits to the east. Otherwise, we do a symmetry according to the y-axis and the seed and the path assembly P still are in the upper part of the plan. Now consider the first time that the path assembly P enters inside the square of width λ1 after the index I3. This index is called I6. From now on, the path assembly P is shortened at position I6. The end of the path assembly P is no more considered or drawn. Now consider the index I5 which is between t and I6 such that the y-coordinate of pi5 is lambda 2 plus 1 and such that pi5 is visible from the east in the segment of the path assembly P from index t to index I6. Two cases may occur. In the first case, the tile pi5 is also visible from the east in the path assembly obtained by shortening p at index I5. In this case, this new path assembly is an exposed one and the first result of the video can be applied. Thus, the path assembly P is pumpable. In the second case, this tile is not visible from the east. Then, there exists a tile Pi1 which is east of the tile Pi5. Thus, this tile is not inside the square of width lambda 2. Moreover, I1 is less than t. Now consider the following window which is in gray. Remark that the tile Pi1 and the tile Pt-1 are in the two different areas delimited by the window in gray. Then the segment of the path assembly P from index I1 to index T has to cross this window. This window cannot be crossed by its north side, otherwise it would contradict the definition of the tile Pt. Since the path assembly P is simple, then the window can only be crossed south of the tile Pi6. Thus the window W of the square of width lambda 1 is also crossed. Then we can define the index I2 as the first time that the path assembly P intersects with W after index I1. Moreover, I2 is less than T. Here the path assembly in gray is obtained by shortening P at index I2. This path assembly satisfies all the hypotheses of the lemma. It exits the square of width lambda 2, then it enters in the square of width lambda 1 and it does not include the tile Pi6. Now, we conclude this video by proving the reset lemma. We remind here the statement of the reset lemma. To apply the previous result, we need only three remarks. First, if the distance lambda is greater than the bound E1, then by the seed lemma, the square of width lambda contains the seed. Remark that we need the seed lemma to be proven before the reset lemma. The second remark is that the square of width lambda is bounded by 4 times lambda. Finally, we define the function psi by applying 4 times lambda times the function psi prime to the distance lambda. Then we can use the second lemma of this video 4 times lambda times, which is the maximum number of intersections between the path assembly P and the window W of the square of width lambda. At each iteration of the second lemma of this video, either P is pumpable or the number of intersections decreases. Eventually, we will find a U-turn and the path assembly P will be pumpable.